Engineers recently tested a medieval peasant construction method against modern building codes, and the results made them uncomfortable. These dirt-poor farmers discovered something about storm resistance that construction companies don't want becoming common knowledge. Here's why that matters to you. Here's something that'll mess with your head. Medieval peasants built houses that are still standing today. 800 years later, no nails, no cement, no power tools. Meanwhile, that deck your neighbor built last summer is already sagging. So what did they know that we've forgotten? Let's start with the obvious question. Why no nails? Simple. Nails were stupid expensive. We're talking a full day's wages for a handful of iron nails. One day of backbreaking labor in the fields just to buy something we grab by the fistful at Home Depot. A blacksmith working all day could only hammer out about 100 nails. Modern machines? 700 per minute. That's not a typo. When buildings got torn down, peasants picked through the rubble like it was a treasure hunt. Every single nail got saved. Some families passed down nail collections for generations. Your great-great-grandfather's nails became your nails. That's how precious iron was. And here's where it gets interesting. This supposed disadvantage forced peasants to get creative. They developed building techniques that actually outperformed nailed construction. Structures that flex instead of snap. Joints that tighten over time instead of working loose. The Romans had concrete, but those recipes vanished when their empire crumbled. Medieval builders were left with nothing. No binding agents. No metal fasteners they could afford. Just wood, dirt, and whatever nature provided. They viewed iron fasteners the way we view titanium. Technically exists, completely impractical for everyday use. But necessity, as my grandfather used to say, is the mother of doing things the hard way until you figure out the smart way. And the smart way started in the forest. Specifically, it started with knowing which trees to cut down. That skill alone took years to master. Finding the right tree wasn't shopping, it was dating. A medieval master builder would walk through a forest the way my grandfather walked through a used car lot. Suspicious, patient, touching everything. He could spend an entire morning staring at one oak, checking its bark for the tight vertical ridges that meant dense, rot-resistant wood. Here's what took years to learn. The angle of the branches told you everything about the tree's future as a building material. Branches shooting straight up? That tree grew fast in competition with neighbors. The wood would be weak and stringy, but branches spreading wide and horizontal, that oak grew slowly, packing tight grain that could last 5 centuries without rotting, and timing mattered more than anything else. Trees cut in winter had almost no sap flowing through them. Dry wood from the start. This meant insects found nothing to eat, and fungus couldn't get a foothold. No chemical treatments needed, just patience and a calendar. But the real treasure hunt? Finding crucks. These were naturally curved branches or trunks that matched the arch shape builders needed for roof frames. Nature did the engineering work. You just had to find where she left it. The catch? A single peasant cottage required around 30 mature oaks. Not just any oaks, specific ones with specific curves and specific grain patterns. Entire forests were managed for generations specifically to grow building timber. Peasants weren't just cutting trees. They were harvesting a crop their great-grandfathers planted. Finding 2 matching curved timbers for one cruck frame could take months of searching through woodlands. Now you've got the perfect trees. But here's where medieval builders did something that sounds completely backwards to modern thinking. Here's where medieval builders flip modern logic on its head. Today, we dry lumber for months before using it. Sometimes years. We're terrified of warping, cracking, all that shrinkage nonsense. But peasants? They grabbed freshly cut green wood and started carving immediately. Sounds crazy. It's actually genius. Green oak is soft, really soft. You could shape a joint with a basic axe in maybe 10 minutes. Try that same cut on seasoned oak and you're there for hours, sweating through your tunic, dulling expensive iron tools. Nobody had time for that. But wait, doesn't fresh wood shrink as it dries? Exactly, and that's the whole point. See, when you cut a mortise and tenon joint into green wood, something magical happens over the following months. The wood loses about 15% of its weight in moisture. All that water leaving causes the fibers to contract. And those joints, they squeeze together like a boa constrictor hugging its lunch. The tighter they get, the stronger they become. It's basically a Chinese finger trap made of oak. The more you pull, the harder it grips. My grandfather used to say some things in life just work better when you stop fighting them. Greenwood joinery proves he was right. Modern engineers tested these connections. A properly dried green wood joint becomes nearly impossible to separate without destroying the timber itself. Meanwhile, nail joints from Victorian buildings are already falling apart after just 150 years. Those peasants knew something we forgot. Sometimes the wrong way is actually the right way. Now, this technique explains the durability, sure, but it doesn't explain how these buildings handled wind loads that would flatten modern sheds. That required a very specific shape borrowed directly from nature. Here's the thing about cruck frames. They weren't invented. They were discovered. Some medieval builder looked at a curved oak tree and realized nature had already done the engineering. The tree grew in an arc, split it down the middle, and you've got two matching pieces that form a perfect Gothic arch when leaned together. Genius? Absolutely. But also just paying attention. These curved timber pairs transferred every ounce of roof weight straight down into the earth. No outward thrust pushing on walls, no need for massive foundations. The arch handled everything. And we're not talking about supporting a few shingles here. A properly assembled cruck frame held 20 tons of thatch using nothing but gravity and friction. 20 tons! That's roughly 4 adult elephants standing on your roof. No nails, no bolts, just wood touching wood. But wait, why curved trees specifically? Builders hunted for oaks growing on hillsides. The natural lean forced the tree to develop denser, stronger wood fibers on one side. It was basically weightlifting its whole life, building muscle against gravity. That compression wood became the strongest part of the frame. The curved shape did something else brilliant too. Flat walls catch wind like a sail. But an arch, wind slides right over it. Forces deflect downward instead of slamming sideways. Box-shaped buildings got flattened by storms. Cruck houses just shrugged them off. Some of these frames still stand in England, not replicas, the originals. 800 years of storms, and they haven't budged. My grandfather's garden shed lasted 11 years before collapsing. Makes you think, but here's what really baffles me. How did they connect these massive timbers without any metal fasteners? The answer involves a joint so clever, it actually gets stronger when you try to break it. So the frame is up. The curved timbers are in position. Now comes the part that actually holds everything together, the mortise and tenon joint. Sounds fancy, but it's really just a rectangular peg fitting into a matching rectangular hole. That's it. No glue, no nails, nothing but wood touching wood. Here's what made medieval carpenters different from your uncle with a hammer. They cut these joints so precisely that you couldn't push them together by hand. You needed a massive wooden mallet and sometimes 2 guys pulling on ropes to force the pieces home. And they did this on purpose. See, the tenon, that's the peg part, was deliberately cut slightly larger than the hole it went into. Maybe a 1/16 of an inch oversized. Doesn't sound like much, right? But that tiny difference created constant pressure between the surfaces. Year after year, decade after decade, the wood fibers stayed locked in a death grip. Now here's where it gets clever. When wind slammed into a wall, those joints actually tightened instead of loosening. The stress pulled the tenon deeper into the mortise. Meanwhile, a nail in the same situation, it's slowly wiggling free with every gust. Medieval carpenters developed over 20 variations of this single joint. 20. Some resisted twisting. Others handled vertical loads. A few specialized in preventing horizontal separation, each one designed for exactly where it would sit in the building. But my favorite detail? Archaeologists found joints that were intentionally left a tiny bit loose, not sloppy, strategic. These buildings needed to sway during storms rather than crack. Flexibility was the whole point. Still, even perfect joints needed something to lock them permanently in place, and what they used instead of nails will surprise you. Here's the thing about medieval builders. They had access to iron nails. They just didn't want them. Oak pegs called tree nails did something iron never could. When moisture crept into a joint, these wooden pegs expanded. They swelled. They created a self-tightening seal that actually got stronger in the rain. Try getting a rusty nail to do that. And the shape? Deliberately wrong. Builders carved square pegs and hammered them into round holes. Not a mistake. Those corners bit into the surrounding wood fibers like tiny teeth. The peg couldn't spin. couldn't wiggle loose, couldn't go anywhere. My grandfather used to say iron was for lazy builders. Now, I understand what he meant. A properly installed tree nail became harder to remove with each passing year. The wood fibers around it slowly merged together through constant pressure. After a decade, you'd sooner split the beam than pull that peg out. But wait, iron should be stronger, right? In perfect condition, sure, but medieval England wasn't exactly Arizona. Damp air, wet winters, morning fog that soaked everything. Iron nails rust in those conditions. They weaken. They shrink inside their holes and rattle loose. Wooden pegs in that same dampness, they swell tighter, get stronger. It's completely backwards from what you'd expect. Then there's draw boring. This technique sounds almost cruel. Joiners would drill the peg hole through the tenon slightly offset from the hole in the mortise, maybe a quarter inch off. When they drove the peg through both holes, it physically yanked the joint together with several hundred pounds of force. Permanent tension, no glue, no fasteners. Shipbuilders used identical technology. If wooden pegs could handle Atlantic storms, a little English weather was nothing. But pegs only work if you have walls to put them in. Now here's where things get a little gross, but also kind of brilliant. Wattle was basically a giant basket woven from hazel or willow branches. Flexible, strong, and it didn't shatter when something hit it hard, but wattle alone wouldn't stop wind. That's where daub comes in. Daub mixed clay with straw, animal hair, and yes, cow dung, fresh cow dung. I know, but before you get too disgusted, consider this. That dung contained natural oils and fibers that made the mixture waterproof. It shed rain for decades without anyone touching it up. My grandmother's generation understood this. They'd say, waste not, want not, while literally plastering walls with manure. And honestly, they weren't wrong. The finished wall dried harder than modern drywall. Way harder, actually. You could punch through drywall in a movie-style bar fight. Try that with wattle and daub, and you'd break your hand. Then there's the insulation factor. These walls performed like 6 inches of modern fiberglass, kept cottages cool during summer heat waves and warm when January winds howled outside. But the really clever part, impact absorption. When hailstorms pelted down or debris flew during gales, wattle and daub flexed slightly, absorbed the energy, then bounced back. Stone walls cracked under the same conditions. Rigid materials break, flexible materials survive. And the cost? Zero. Literally nothing. A family gathered everything from surrounding land, clay from riverbanks, branches from managed hedgerows, dung from their own livestock. Weekend project, 4 walls done. Makes our expensive building materials look pretty silly, doesn't it? So the frame was strong. The walls could take a beating, but none of it mattered if water got through the roof. And medieval peasants had that covered too, literally. Here's where medieval peasants pulled off something that still makes modern roofers scratch their heads. Thatch. Just straw. Piled on a roof. Sounds primitive, right? Like something you'd throw together if you ran out of real building materials. But here's the thing. A properly built thatch roof lasted 40 to 60 years. Some lasted longer than the people who built them. The secret was weight, or rather, the lack of it. Thatch weighs about 7 pounds per square foot. Clay tiles? Nearly double that. So every beam, every joint, every cruck frame underneath carried half the stress. My grandfather used to say the best way to win a fight was to not show up. Medieval builders figured out the best way to build stormproof was to build light. But lightness alone doesn't keep rain out. This is where the engineering gets clever. Each straw stem has a natural waxy coating. Water hits it and runs down, just like rain sliding off a duck's back. And when you layer thousands of these stems at steep angles, you create a waterfall effect. The water never sits still long enough to soak through. Now, about that steep pitch, those roofs angled at 50 to 55 degrees weren't just traditional. That precise angle accelerated rainwater off the surface before it could penetrate. Any shallower and you'd have leaks. Any steeper and wind would rip it apart. Speaking of wind, here's something counterintuitive. Gale force gusts actually press thatch tighter against the roof structure. Modern shingles catch air underneath and peel off like banana skins. Thatch just hunkers down. The insulation worked both ways too. Interiors stayed cool in summer, warm in winter. But none of this mattered without a solid foundation. And that's where things got really creative. Here's the thing about medieval foundations. They didn't have concrete. No rebar, no cement trucks, and yet their buildings stood for centuries on ground that would crack a modern slab in 5 years. How? They worked with the earth instead of fighting it. Corner posts sat on large flat stones called padstones. These worked like snowshoes on powder snow. Instead of a narrow post punching down into soft soil, the stone spread that weight across a much wider area. Simple physics, really. But here's where it gets clever. Modern foundations try to stay perfectly rigid. Medieval builders, they let their structures move. Frost heave happens when frozen ground swells upward in winter, then drops back down in spring. Fight that movement with a rigid foundation and something cracks every single time. Medieval structures just rode it out. The whole building would rise a bit in January, settle back down by April. Those flexible joints we talked about earlier, they absorbed that seasonal dance without breaking a sweat. Some regions used a technique called earth-fast construction. Builders charred the bottom of posts with fire, then buried them directly in the ground. That charcoal layer resisted rot and insects for 30 to 50 years. Not permanent, sure, but replacement was straightforward when the time came. And drainage? They handled that too. Gravel-filled trenches beneath walls acted like primitive French drains, channeling groundwater away before it caused problems. Buildings went up on slight slopes, so rainwater just walked itself off the property. No pumps, no pipes, just smart positioning. My grandfather's barn from 1942 already has foundation cracks. Meanwhile, medieval cottages built on these simple techniques are still standing. But a solid foundation means nothing if the roof blows off. And medieval builders had some seriously counterintuitive tricks for defeating wind. Here's the thing about medieval builders that modern architects are just starting to appreciate. They didn't fight the wind, they redirected it. Hipped roofs, the ones sloping down on all four sides, reduced wind uplift by 40% compared to gabled roofs with those flat-end walls. 40%. That's not a small improvement. That's the difference between keeping your roof and watching it sail into your neighbor's field. But wait, it gets cleverer. Those heavy eaves extending past the walls, not decorative. They forced wind to curve downward rather than sneaking underneath and lifting like a massive hand flipping a pancake. My grandfather used to say good design looks lazy because it makes hard things easy. Medieval roofers understood this instinctively. Now here's something that seems almost too smart. Some regions built asymmetrical roofs, one side short and steep, the other long and gradual. The short, steep side always faced the direction storms typically came from. Wind would hit that angled surface and slide right over instead of slamming flat. Inside the structure, diagonal timbers called wind braces transferred sideways forces straight into the ground. Without these, strong gusts would push the whole building sideways like a drunk stumbling home. Not ideal when you're sleeping inside. Roof trusses were assembled completely on the ground first. Every joint tested, every peg driven tight. Only then did the village raise them into position. Because discovering a loose joint during your first major storm, that's a problem you can't fix from bed. And get this, buildings were deliberately positioned with their narrow ends facing prevailing winds. Less surface area means less force. Simple geometry that kept families alive. But none of this mattered without help, because raising those massive trusses required something no single family could provide. Here's the thing nobody talks about when discussing medieval construction. You couldn't build one of these houses alone. Not because you weren't skilled enough. The physics simply wouldn't allow it. Raising a single cruck frame required at least 20 adults working in perfect coordination. One person calling commands, others pulling ropes, everyone pushing at exactly the right moment. Miss the timing, 800 pounds of oak comes crashing down, possibly on your neighbor's head. So house building wasn't a construction project. It was a community event, almost like a barn dance, except heavier, and with more splinters. Villages developed this fascinating specialization system over generations. The Miller family, they'd been thatchers for 200 years. The Wrights, and yes, that's where the name comes from, handled all the joinery. Everyone knew their role before they even showed up. A peasant family expecting to build alone would have been like someone today trying to move a piano up 5 flights of stairs by themselves. Technically possible, practically insane. But here's where it gets interesting. This cooperative system created something economists call obligation networks. You help me raise my walls this month. I help you rethatch next spring. Your uncle brings the best daub mixture. My cousin knows where the straightest hazel grows. The whole village became interconnected through building debts, and these debts functioned as medieval insurance. Your cottage burns down? Nobody files a claim. They just show up. Because they owe you, and because someday they'll need the same help. Knowledge passed through this system too. No blueprints, no written manuals, just experienced hands guiding younger ones, the same techniques flowing through families for centuries. A fresh cottage shell could be weather-tight within 1 month using this organized community labor. But raw labor alone wasn't enough. These buildings needed something else to survive 800 years. Here's the part that blows my mind. Over 5,000 medieval timber frame buildings still stand in England alone. 5,000. Meanwhile, houses built in the 1970s are already falling apart. These structures have survived 8 centuries of storms, wars, and that one neighbor who always borrows tools and never returns them. What's their secret? Flexibility. Those joints we talked about earlier, they don't just handle storms, they accommodate centuries of ground settling without cracking. The earth shifts. The building shifts with it. No problem. But there's more. Those wattle and daub walls actually breathe. Moisture moves in and out freely. Modern buildings, we seal them up tight with vapor barriers and paint, then act surprised when mold takes over. Medieval peasants accidentally figured out building science that we forgot, and the wood itself fights back against decay. Oak heartwood contains natural chemicals called tannins that basically poison any fungus or insect trying to eat it. No treatments needed, no chemicals applied. The tree did all the work centuries ago. Now here's the really clever bit. When something did eventually wear out, builders could swap individual pieces without touching the rest. One rotten beam, replace it. The structure keeps standing. Try that with a modern house where everything connects to everything else. I've seen restoration workers pull out a single timber, slot in a new one, and walk away. The building barely notices. Modern earthquake engineers now study these medieval structures to understand flexibility principles. Turns out peasants who couldn't afford nails accidentally invented seismic-resistant design. They had no choice but to build things that moved. And that movement is exactly why these buildings outlasted everything we've built since. 800 years, still standing. Not bad for people who couldn't buy a single nail.